Hey everyone, welcome to the next video for section 7.9. So in this video, we're going to see our good old friends coming back for solving non-homogeneous problems. We're going to see undetermined coefficients and variation of parameters making their appearance again for solving non-homogeneous problems. So again, like I mentioned in the last video, I'm just going to go through the brief outline of the methods here. And then the next video is going to be an example where I solve one problem that's non-homogeneous using all three methods we've done so far, which will be diagonalization, undetermined coefficients, and variation of parameters. So let's go in and start talking about these general methods. So method 3 is going to be undetermined coefficients. So again, we're trying to solve x prime equals ax plus g of t. And as before, for undetermined coefficients, we generally want a to be a constant matrix because outside of that, it's really hard to start guessing things. And the idea is the same as before. It's guess a form for x of t based on what g looks like. And again, g is going to have to be something that's like exponential functions, polynomials, sines and cosines, or some combination of them. Because that's really the only things we can actually guess and try to solve a system by this way. And then the only real difference is when we plug in coefficients, we're going to plug in a vector for each coefficient instead of just a number. So right, for before, when we had an e to the t on the side, you would guess e to the t, and you would guess a times e to the t. Well, now instead of guessing just a to the t, you would guess a vector a times e to the t, and so on down the line. You have to remember to always include all the coefficients down, because like we saw for our generalized eigenvectors part, just because the one thing goes to zero just because something solves homogeneous doesn't mean you can't include it. You just have to include it with another vector and see what happens. So when you're guessing, include a vector of coefficients on each term. So for instance, if g of t looks like t e to the t and sine t, then what you're going to guess is a vector a times sine t for the bottom part, plus a vector b times cosine t because sines give you cosines, plus a c times t e to the t, plus a d times e to the t. So this will get really complicated really fast, but the idea is the same. You're going to guess those, you're going to throw it into your equation, do all the multiplication and derivatives out, and then see what you need to pick for all of your constants to make you satisfy the equation. Pick constants to satisfy the equation. And note, in this case, we actually have 8 constants because each vector there is going to be a 2-component vector. So there's 2 constants in A, there's 2 in B, there's 2 in C, and there's 2 in D. This is going to give us 8 constants to solve for, so we should end up with 8 equations at the end of the day for getting these constants. All right, so that's the idea for undetermined coefficients. It's the same thing, guess a solution, plug it in, find your constants, and see what you get. Now the last method we're going to talk about in this section for this is variation of parameters. So this idea is the same as before, and this is going to go back to our fundamental matrix stuff from section 7.7. So I'm trying to solve x prime equals ax plus g of t, and I want to let capital X be a fundamental matrix for the homogeneous problem, x prime equals ax. This is similar to saying I want to get my general solution for the homogeneous case in second order equations, and then we're going to use it to solve the other ones. Now we know that any solution to x prime equals ax is given by x, this fundamental matrix, times some constant vector c, where c is a vector c1 through cn. Right, we did this in 7.7, talking about what fundamental matrices do. If you multiply this by a constant vector, you get your general solution to the equation. So now what I want to do is do the variation of parameters thing again, where I want to now solve the non-homogeneous problem using that I want to now vary my constants into functions and see what happens. So for variation of parameters, we guess this matrix x of t times an unknown function vector u of t, replacing our constants by varying them into functions u of t, and plug into the equation. Now if I plug that into both sides, what do I get? Well, I get on this side, I get x of t times u of t prime equals a times x times u of t plus g of t. And if I do product rule on the left-hand side here, I get x prime of t u of t plus x of t u prime of t equals ax u of t plus g of t. Now, since x is a fundamental matrix, we know that it solves the same ODE. So x prime equals ax, which means this term and this term are going to cancel out. Because x is a fundamental matrix, each column solves the system, so the whole matrix solves the system as a whole. So that means these two make 0, which means I'm left to solve x of t u prime of t equals g of t. Now, from a theoretical standpoint, we know x of t is invertible, so I can invert x of t to the other side to get u prime equals some function of t, which is x of t inverse times g of t. I can then integrate both sides and solve for u that way. But from a more computational point of view, this is now a system of equations for u prime as a vector, solve it, then integrate to find u. And then once I have u, I get my solution. And then get solution by x of t equals this fundamental matrix times u. So the idea is the same that we did before for variation of parameters, right? We plugged in this thing, we varied our constants into functions, threw it into our equation and saw what happened. The end result was we got a system of equations for the derivative of our unknown functions. We solve that system for the derivatives, then integrate them to get the actual functions, and then get a solution by plugging that in again as before. So if you work this out and look at it in the second order system, it actually comes out to be the exact same method of variation of parameters that we did before. But in any case, that's the idea for this one. That we can solve these things both with undetermined coefficients and variation of parameters using the same setups we had before, just writing them out in these different details. All right, so that's it for this one. The next one is going to be the example where I take a single system that's non-homogeneous and solve it using diagonalization, using undetermined coefficients, and variation of parameters, so you have all those methods work out all at once. So thanks a lot for watching this one, and I will see you in the next one.